interesting. Right, we're going to look at today 3.2, how to calculate what is called measures of spread. On Monday, we looked at measures of centre, which is basically things like the mean or the median. And that number gives you an idea of the typical person in the group. So there's a second measurement called the measures of spread, and there are 3 of them. They're called the range. Very simple to calculate the range. You basically just take the biggest number and you subtract the smallest number. Although it's very easy to do, it's not that practical. It's not sophisticated enough to get you the gist of what you want. The second one is called standard deviation. Very often, the letter S is used for it. You'll also see in some texts they use the letters SD. So if you ever see S or SD, they're talking standard deviation. That's what they're giving. And these we're talking about, we're doing them in a sample right now. And the third one is called the interquartile range, called IQR. Its full title is interquartile range. IQR for short. Now, these 3 different measures of spread are necessary because it was pretty quickly discovered that just using the mean didn't give you the whole story about what your data looked like. Because you could have 2 different sets of data with the exact same mean or median, but looked quite different from each other. One of them could be all the numbers are really close to each other, and the other could be the numbers are all spread apart. And they could still have the same mean or median. So let me do an example of that. Suppose there were 2 classes. One was called Class A, and the other one was called Class B. And we collected some data on them. Let's say it was the ages of students in these classes. And just to make my life easier, we're going to have very small classes, right? So we'll put it at 21, 23, 24, 27, 20, 19, 17, right? So these are the 7 people that were in that class. And this is the second class. And this is the second class. Now, in this particular data set, if you calculated the median, it would be 21 in both cases. You agree? The middle number, the median, is 21. But these 2 classes are quite different. Would you agree that in Class A, everybody is pretty close to each other in age? There's not an awful lot of variation, is a word that typically might be used. Would you agree that Class B is all over the place? There's a lot of variation in who's in that class. So if I just told you, hey, I teach 2 statistics classes and the median age of both of them is 21, if that's the only thing I told you, wouldn't you come under the false impression that both classes were pretty much the same? Right, the middle age is 21. They're probably just, you'd hardly be able to tell the difference in ages. But in reality, there was a big difference. So we need a number that measures how spread out things are. And there's actually 3 of them. So I'll keep that data set and then I'm going to return to it once we've shown you how to do these, and we can do a kind of calculation. Actually, I don't even need to remove it for at least one of the calculations. Let's calculate the thing called the range of the data. Right. Well, the range of class A. Oldest person is 27, youngest is 17. We would say that the range of that class was 10 years. That seems reasonable. Big takeaway, small, 10 years. Now, if we did the range for the second class, you would have a 51-year-old takeaway an 11-year-old, and that's 40. Isn't the range of this class 4 times bigger than the range of that class? So in a way, that is a measurement. Isn't that a number that allows you to see the range of class values? If that number is very small, doesn't that mean everybody is really close to the mean or the median? And if that number is really big, it means there's a lot of variation, right? A lot of numbers are way over at big side and other equally, probably, often numbers in the tiny side. And that's how you calculate the range. You can't get much simpler than big number take away little number, right? Okay, and we'll talk later about why the range, apart from being easy to get, why it's not really used much because of that. So the second fella I'm going to show you how to do is called the interquartile range, IQR for short. Now, to be able to do this, I'm going to take my data set, which you can see, and there's 7 numbers, and then you find the median, which is this guy here. The median is also called Q2. That's another name for it. And I'm going to cover up the median. Oh, here we go. Now, do you see that what I've now done is I've split the data into 3 big numbers and 3 small numbers. The middle, or the median, but I'd probably use the word middle, the middle of the first 3, that guy's called Q1. And the middle of the big 3, which in this case is 24, is called Q3. Does Q2 seem to make more sense now when you think about why it's called Q2? First quarter, second quarter, third quarter, right? So the interquartile range, you find Q3 and you subtract Q1. So Q3 is 24. Q1 is 19, and I get the interquartile range is 5. Are we comfortable with how I did that? Right? You find the mean and the median, and then you separate your data into 2 chunks. Now, that's the interquartile range of A. If we find the interquartile range of B, well, cover it up. This guy is the middle of the little numbers, so he's called Q1. And this number here, right, that's the middle of the big numbers. And if we do Q3 take away Q1, we have 41 take away 12. Oh, it's that 28, 29. And isn't that reflecting what the data was showing? Isn't this number much bigger than that number? So that is a reflection that this data set is much more spread out than that data set. We like the concept? Right. So because the interquartile range is a little bit fiddly, I'm going to have to show you 2 versions of it. This version that I've just shown you was when there's an odd number of data points, like there's 9 numbers or 29 numbers, right? But you can calculate it, but you just have to be a little bit more careful when there's an even number of data points. So this is just a totally random set of data in order: 1, 3, 3, 7, 9, 11, 15, 21, 23, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I need another number, 10. Right? So this is a sample size of 10. Check it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, remember when it was an odd number, we found Q2, well, we covered it up, and that way we could split the data into 2 equal halves. We're going to have to figure a way of making it happen when there's an even number. When there's 10 numbers, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Isn't the median halfway between the 9 and the 11? Remember that happened before. And so in that case, don't we just call it 10? But in this case here, do you notice that the pen doesn't destroy any of the data? Basically, if I put my pen here, can you see the 5 big numbers on this side of the wall and the 5 small numbers on that side of the wall? That's a little bit different when there's an even number. When there's an even number, doesn't the middle number get killed? You know, you brick over the number by your wall. Whereas in this case, don't you kind of build the wall between the 2 numbers? Because what you're trying to do is split the data into 2 equal halves. Now, of the lower half, which one of these numbers is Q1?
3.
You all agree it's that 3 there? On the big side, which one of them is Q3?
21.
Do we feel comfortable about how you would create this from you know, when it's a small data set, this is kind of what your working is going to look at. All you write into the, you know, the homework is 5 and 29, but you have to do stuff to get that, right? So the what's went red on this? The interquartile range here is Q3, take away Q1, which is 21, take away 3. In this case, 18 would be the interquartile range. Right, you feel comfortable about calculating the range? The range is just big take away small, that would be 40 in this case. Do you feel comfortable about calculating the interquartile range? Different measure is spread. So far so good, I think. Right. I just thought of a situation. I'm going to put it in. This is the last variation on interquartile ranges. In this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so there's 12 data points. So 1, 2, 3, 4, 5, 6. There's going to be your wall, right? And so the median is going to be 12. Do you see that in this last situation, aren't there 6 little numbers and 6 big numbers? Right, there's 6 numbers here, and there's 6 numbers here. Now I need to find Q1. You see the problem? Isn't it halfway between those 2 guys?
Isn't Q1 just 4?
Exactly. And over on this side, won't it be between
20.
those 2 numbers? And it's 20. Does that seem a sensible adaptation to what you have to do based on how many data points? So just for completeness sake, the interquartile range, Q3, take away Q1, 20, take away 4, and the answer in that case would be 16.
I have a question still on this.
Yes, go for it, Denise.
What if the Q2 was in between 2 of the same numbers, like in the first or the set before we had 2 3s?
Oh, like it was 11 and 11 or 13 and 13, like
yes.
that? All you would do is keep the wall there, right? The dotted line would still be there. Right? So in case you're wondering what she's saying, if I pick her up right, imagine the data set was 2 13s, right? Technically speaking, it's between 2 13s. So Q3 would be 13, but that wall would still be there. You'd still keep it in the same location. So it's not that you would destroy the 13s, you would just have this invisible partition, And the reason you need that partition is, don't you have to find some way to evenly split your data into two separate groups? So you either do a wall between two numbers, and that's why you separate them, or if there's an odd number of numbers, you kill the guy in the middle by building the wall right over it. Does that answer your question, Denise?
Yes, thank you.
Okay, good question. Right. There was third list, wasn't there? There we go. There's a guy called standard deviation. Now you can do the range by hand, as long as there's not too many numbers. Would you agree you could do the interquartile range by hand? You will probably never, ever do the standard deviation by hand. You will use your calculator to do it, and I'm going to show you in a few minutes how to do that. Or you will use the salt button. Remember that salt button, and you just do data description, and one of the data points, one of the statistics it will tell you is the standard deviation, right? But I'm going to show you only once how you would do it by hand, but I don't want you to actually do it this way. I just want to show you what it is like by hand, so that when we get it to do in the calculator, you're going to say, I am glad the calculator done that all for me, because I certainly didn't want to do it the way he showed me, right? So it's not complete magic. So I'm just going to pick a small data set and show you how you would calculate by hand the standard deviation. So 1, 5, 7, 8, 11, that's 6, 13, 23, 32, 32, I want 14, 32. I'm trying to make these numbers nice. If I just randomly pick a number, I'll make it even worse than it is. 6, 13, 21, 32, 42, 42. That's good. No, I think that'll do. So here is our data set. You typically do these questions as a table. And the first thing you do is you basically write down one row for every single one of these numbers. Let me double check. 6, 13, 21, 31. Oh, shooting space. 6, 13, 21, 31, 32, 42, 48. We're cool. And you calculate the mean. And the mean is 42 divided by 6. The mean ends up being 7. So the first guy after the data is a guy called deviation, or deviations. And you get it by taking your data and subtracting the mean. So 1 take away 7, 5 take away 7, 7 take away 7, 8 take away 7, 11 take away 7, and finally 16 take away 7. And that's your deviation. You then square all those numbers. You then find the total of these guys. 6, 10, 11, 17, 18, 9, 10, 11, 12, 13. So far, so good. Then what you do is you take this number And it's got a name, it's called a variance. And you take this total and you divide it by 6. And 6 because there's 6 numbers. So 138 divided by 6. Wow, that was just sheer luck. You got 23. And the standard deviation of the population, because I've just shown you how to do the population standard deviation, is the square root of this guy. So the square root of 23 is about 4.8. Now, can you imagine trying to do what I just did for a really ugly X bar like 6.98 with 20 numbers? Wouldn't you be spending all day just doing one blinking question, one single standard deviation? So we don't typically do standard deviation by hand, but this is how you would do it by hand. Now, this is the population standard deviation. There is a second standard deviation called the sample standard deviation. It's the exact same calculation, except one difference. Do you know how here you divide by n how many data points you've got? When you do a sample standard deviation, you divide by 1 less, so you'll divide by 5. But you'll still take the square root and everything else. So there is a lot of work in doing that. So don't you want to find out how to do it on the calculator? So you don't have to do tables and square things, right? I would have thought I'd sold that much better than I ended up selling it. I would be hoping you're thinking, God, yeah, please show me a better way than that. Right? I don't want to do that. I certainly don't want to do that when there's 20 numbers, right? You know, there should be a health warning on a question if that's what you had to do, right? So I'm going to get my TI-84 up and running, and hopefully you should see it, or you will in a few moments. And if you've got a TI-84 handy, I strongly suggest that you do that. Okay, can you see the emulator program called Wibbit? I've got a link to it on Canvas. And it basically does the job of your calculator. We need some data here just so that we can do it with some numbers. So I'm going to ask you to, how many people do we want? I want about 8 people thereabouts to volunteer their age. So if you call it out, I'll write it down.
21.
I hear a 21.
16.
Another one?
17.
22.
17.
23.
23.
Up. Another 23. Another one? 64. 9. Right. We got 8 numbers. So you got your calculator. The first thing the calculator needs is your data, right? Those 8 numbers. You know, you have to put them into the calculator in some way. So you hit the start button. You see it there? It's where my little mouse pointer is. You hit the start button. And option 1 says edit. You see that option 1 thing? And you hit enter. And then you just type in your numbers in any order. It doesn't need to be big to small. So if you gave me your age, it should be, if I wrote it down correctly, one of these numbers. Lost a place, 23. Oh, and me. Okay, so you got your data in. Now you hit start again. You move over to calc. And here it has a thing called 1 variable stats. You see that heading, 1 variable stats. Now my machine is a little bit older than yours, so when I hit this, you might see something a little bit different, but it's essentially the same thing. So when I hit this, I have this option. It says 1 variable stats in a little cursor. what the calculator is saying to me, where am I going to get these numbers that you want me to find the standard deviation of, right? That thing, or whatever you want. And for me, I have to tell it it's in L1, because that's the column I put it in. And to do that, you hit blue button 1. Now, for some of you, you're looking at a funny little menu. And if you're really lucky, doesn't that menu already say L1 in it? So all you need to do is hit enter, 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 and paste at the bottom. In my case, I hit enter. And here we see a summary of lots of statistics to do with that particular data set that I put in. For instance, the mean of that data is 25.7, roughly, right? We're doing everything in one decimal place. You see this guy called SX and the one underneath it called Sigma X? You see SX and Sigma X? SX is the sample standard deviation. So that's the 17.1 that we were looking for. And the one underneath it is called the population standard deviation, and that's 15.8. You see they're slightly different because one divided by 7 and the other divided by 8. That's why they're slightly different values. And that's where you get your answers from.
Wait, Professor,
SX,
which did you call the bottom one?
say again?
What did you call the second one again? Sorry.
The second one is called the population standard deviation. And the one above it, the one that starts with an S, is called the standard, the sample standard deviation. Here's some other stuff. Do you notice it says n equals 7? So evidently I only wrote down 7 numbers, but I'm going to keep it because I don't want to redo it. Do you see that the smallest number was 16? That the Q1 was 17? That the median was 21? That Q3 was 23, and that the maximum was 64. Do you see you actually get everything? You even get Q1 and Q3, which means if you just subtract them, won't that be the interquartile range? And don't you get the maximum and the minimum? If you subtract them, won't you get the range? Do you see this whole process allows you to get all of the answers in one place? You don't even need to find Q1 and Q3. Calculator does it. You certainly would need it for the standard deviation, just because of how messy it is. But it's kind of nice to know it does all of it, right? So can you imagine a question that might have 20 numbers in it, and they're all jumbled up? If you wanted to do the interquartile range, that would take a fair amount of time. Wouldn't you first have to write down the numbers from smallest to biggest? And then find the middle to split the wall, right? The wall thing. And then Q1 from the first group, right? And Q3 from the, you know, it's time consuming. In this, don't you just need to type in 20 numbers and the rest is pretty much finished? So I'm trying to sell the calculator to you, right? That it is going to help you get the answers in a much more efficient way. And it's accurate, provided you type in the data the right way. You're going to get the right answer every time. Any questions about that, or will be comfortable about how you use the calculator to do those kinds of questions? If we're good, then I want to move on. Last chance. Any questions before I move on? So I guess we're all pretty comfortable with what we've done. Good. I like comfortable. So there's quite a lot of things that you can get and properties that you can get from range, standard deviation, and interquartile range. So let's look at some of the properties. Let's look at what do outliers do? In other words, suppose you have a data set and you have Bill Gates in it. How does it affect the range, if it affects it at all, standard deviation or interquartile range? Okay. So if you have a set of data and there is one large outlier, Well, let's take a very small data set so I can do this. 1, 3, 10, 20, and 100. Compared to those four numbers, isn't this one huge? Right, 20 to 100, right? It's 5 times bigger. In this world, right, if you were doing this particular world, actually, I'm going to have to put in maybe a few more numbers. Yeah, that'll do. Right, one large outlier. It's Guy 100. What will the effect be on the range? Well, the range is 100, take away 2, the range is 98. Great. What's the standard deviation going to look like? Well, I'm going to put that in the calculator in a few moments. And what's the interquartile range going to look like? Well, interquartile range, I think I could do it without the calculator. But since the calculator's here, right? Might as well just use it, right? So switch it on, clear that out, hit start, go to number 1, and the numbers are 2 and 4 and 8, 10 and 20 and 21 and 100. And then hit start a second time, move over to calc, choice number 1, and then just blue button 1, and I'm done. So let's see. The sample standard deviation, S, is about 34.5. And interquartile range. Well, if I'm being lazy about it, can't I just go to the bottom and get the numbers I need? And so the interquartile range, which is basically 21 take away 4, is 17. So far, so good. Now, what's not obvious yet, although it should be kind of obvious, isn't that outlier having a really bad effect on the range? Because if you think about it, without that outlier, isn't the range only 19? Right, 21 take away 2, the range is only 19. So for comparison, I'm now going to take that data set and I'm going to remove the outlier. Now, I know that means that I've got a smaller sample, but that's fine. We're going to get the range, the standard deviation, and the interquartile range. Before I even calculate them, do you think the range is going to be bigger, smaller than it used to be, which was 98?
Smaller.
Agreed. Less obvious. What do you think the standard deviation is going to be, bigger or smaller, now that you've removed this guy?
It's probably gonna be smaller as well.
And it will be, and we'll discover that's a property. Big outliers, any kind of outlier, small ones included, make the standard deviation really big. And one number shouldn't do that. Doesn't one big number make the mean really big? And don't we normally kick it out because of that? Now, interquartile range.
It'll be close, but not.
It won't move much.
Yeah.
Agreed? Is that what you would think?
Yeah.
Common sense? And that's true. Outliers do not affect the interquartile range significantly. They just don't. You know, with it or without it, it's probably not going to be hugely different. I should expect a fair change on the other two. So the range is 21 take away 2, that's 19. I can now return to my calculator and I can hit start and I can hit edit, but I'm going to do this. I don't like 100. I want 100 to go away, so I'm going to hit delete. That means I don't have to redo the data. Do you see I've basically just removed it? You know, sometimes you put the data in and you put in 42 and then you get distracted and you put in a second 42, but it's too late. It's not too late. Just go to it and hit delete. It'll go away. So start button, edit. Oh, shooting space. Start button, calculate. They're better. And number 1. And it's now gone from 34.5 down to essentially 8.0. Would you agree that's a really big difference? It's like a quarter of its size. Right. Now, what about the interquartile range? Well, if I scroll down this data, the interquartile range, Q3 take away Q1, let's see what we get here. It's 20 take away 14 equals 16. Would you agree that there's not a big change? Used to be 17, now it's 16. Nothing. Used to be 98, now it's 19. Big difference. Used to be 34 and a bit, now it's 8. So the answer to what do outliers do? They make the range and the standard deviation larger, noticeably so. But they don't affect the interquartile range. Isn't that the same property that mean and median have? Remember on Monday when we calculated the mean with Bill Gates, it was huge, but when you calculated the median with Bill Gates, you know, an outlier, it had no effect. So not only do outliers affect the mean and standard deviation, they don't affect the median or the interquartile range, which is why in quite a lot of situations, the interquartile range is your friend. It means that you can have quite ugly Bill Gates data, but the interquartile range is not going to be mucked about with it, right? You can still use the numbers that are realistic. You shouldn't use the standard deviation if Bill Gates is around and your data sample is really small. Actually, you probably shouldn't use it even if your data sample is really big, because isn't Bill Gates got a really big number and he can affect even 1,000, you know, 100 million split amongst 1,000 people is still an awful lot of money, right? It still affects it. Are we good? Comfortable? Okay. Then that's one of its properties. Suppose I take the same data set. I'll take this one without the outlier now. I'll use that as my kind of working data set. And we get to its range and its standard deviation is sample and its interquartile range. And this is was 19, this was 8, and this was 16, right? Suppose I take all these data points and I add 10 to them all. So this number becomes 12, this becomes 14, this becomes 18, 20, 30, 31. I could do the calculations, but I'm not going to. I'm going to use a fact that I already know what the answer is going to be because this is a property. If you add 10 to all the numbers, will the range get bigger, smaller, or stay the same? That's your three choices. Bigger, smaller, or stay the same?
Stay the same.
Correct. Will the standard deviation get bigger, smaller, or stay the same?
It'll just stay the same.
and stays the same. Now you might say, but the numbers are different. Yes, the numbers are different, but aren't they spread out the same way that the original numbers were spread out? Isn't the gaps between them the same? That's what we're measuring, right? How spread out the numbers are, not particularly what they're equal to, but just how they are spread out amongst themselves. Couldn't I add 100 to all of these numbers and it would just be the same group of numbers, but like on the number line, 100 to the right? Not really spreading out anymore. Well, that's adding 10. Right here. Also subtracting 10 has no effect. Suppose I doubled all the numbers. 4, 8, 16, 20, 40, 42. I doubled all the numbers. I don't need to do any calculations because I know the property. If the life was simple, what do you think would happen to the range, the standard deviation, and the interquartile range if everybody got double what they used to be?
Would it would it get doubled?
It does. So double it, double it, double it. So adding numbers doesn't affect how spread out they are, but isn't doubling them kind of pulling them apart, making them twice as spread out? And I won't do this one, but if I said half the numbers, wouldn't half the numbers crunch them together a little bit? And it would be half all those values. So it's nice that they all go the same road, right? They all double, they all half, they all stay the same, whatever it might be. Usual question, are we good with that? Can we move on? Okay. For no particular reason, because it just came out in my head, I want to get some of the notation out of the way. When you do standard deviation, if you calculate it using every single person in the population, the standard deviation uses that symbol. I've exaggerated the top. It's called sigma. If you do it with a sample, it's called S, right? Range doesn't have a name for population. It's called the range from the population and it's called the range in the sample. It doesn't have funny Greek letters. There is a guy called variance. Variance in the population is called sigma squared. And in the sample, it's called S squared. If you had a sample standard deviation of 10, you would have a sample variance of 100. You basically just take the standard deviation and square it. So you're going to get questions where it doesn't just say find the standard deviation, A. It might also say find the variance. Well, wouldn't the variance in this case be 64? Sample deviation squared, right? I would go with that naming system. So if somebody says, find sigma, don't you know you're going to find the population standard deviation? If somebody says, find S squared, don't you know you're going to get the variance of the sample? You're going to get the S from the sample and square it. Cool. Right. You know you are allowed to say, no, we're not cool. Could you say that a better way? Because it made no sense to me. You know, that is allowed, honest. Apart from taking 10 points off your final grade, it won't affect me in any way whatsoever, right? At least Erica knew that that wasn't accurate, right? Okay. I think things are going pretty smoothly. I mean, the lack of questions is normally a reasonable sign. There are a couple of other things that are going to pop up, but I think it's probably time that we had a look at some of the homework questions, because very often it's useful to see how the book or how the homework gets asked, because they do have their own kind of unique way of doing things sometimes. And here we are. Okay, so I just need to make sure that you're seeing what I'm saying. Right, I guess I should scroll up. I'm just going to get questions 1 to 3 out of the way. It's the same question for everybody. It says, which average, the mean, the median, or the mode is associated with the standard deviation? Do you remember that one and only time I did it by hand? Which one of those 3 was part of that calculation?
The mean.
And that's the end of question 1. We've just finished talking about this. Oops. What is the relationship between variance and standard deviation? The standard deviation is half the variance. The standard deviation is twice the variance. The standard deviation, they have just phrased it the reverse of how I phrased it. Didn't I say the variance was the square of the standard deviation? Well, if you turn it on its head, isn't the standard deviation the square root of the variance? So it's worth to look at homework questions. It's the same information, right? They've just turned it on its head. And let's see if we can do the symbols then. What symbol is used for standard deviation when it's a sample statistic? And what symbol is used when it's a standard deviation from a population parameter? Well, is it this one? Or is it this one?
Second
Top of the,
one, the
yeah,
bottom.
the bottom one, right? Now, the next group of questions from what I can see are pretty standard. The way they phrase it isn't, but don't worry about that. Find the range. Well, you could do that in your head. When it says find the standard deviation of the sample and find the standard deviation of the population, I would be doing, the only way I would do that is, won't we put these numbers into my calculator? What did the calculator call the sample standard deviation? So what thing do you look for to write the number down? Right.
SX.
So, yeah, so in this guy, you're going to look for the SX, right? Don't type that in, but the SX is, I don't know, 12.25. And then the other one is 8.97, right? Whatever it is. Can you see that question is basically saying, put some numbers into the calculator, calculate the population and the sample standard deviations. And if they want 2 decimal places, remember, that's what you need to round off. If you round off to 1, it's going to say you're wrong. Question 5 is really the same question. Puts you through a whole load of steps. Oh, here's a good one. Each of the following 3 data sets has a mean of 10. I'm glad you told us. Without doing any calculations, order them according to increasing value of standard deviation. So which one of those 3 is got the smallest standard deviation? 1, 2, or 3? Okay, suppose I take out the word standard deviation. Which one of those 3 data sets are the numbers closest to each other?
1.
See, makes sense when you say it that way then. 1. Of the other two, which one of them is the most spread out? A little bit harder, but one of them is more spread out than the other. And spread
2.
out means from the middle. So which one?
3.
3.
I agree. So the answer is 1, 3, 2. And you can use salt if you like, but I mean, without doing any calculation, seems a bit of a cheat then if you're not doing it that way. And then you just try and pick one of them. And what's going to happen here? Here's a data set. Put in there standard deviation. Now, just to show you that the calculator is great and so does salt, because not all questions have salt, so that's why you've got a backup plan. If I hit the salt button, comes over here. If I hit descriptive statistics, can you see standard deviation is 4.6? So that was even quicker than the way I showed you. So that number was 4.6. Oh, I should look, how much accuracy did the one? Oh, 4 decimal places. 4.6043 then, just to keep them happy. Now, suppose you added 2 to all those numbers. What's the new standard deviation?
It's just 4.6043.
Can you pretend, can you pretend that you did it? But won't that be what you'll get? If you don't believe me, you'll physically do it and get the answer and you say, hey, he said that, it worked, right? Now, if they say, you know, what is going on here? Well, if you add the same constant C, right, if you add the same number, don't they remain the same? So you pick the top one. Here's some data. This time you're going to multiply it. Here's a question to do with outliers. So I'll let you figure it out. Oh, our new guy in town. There is a fella called, yeah, we've got plenty of time, good. It's called the coefficient of variation. And there is a guy that I'm going to check here, but it basically says this, although you can't see what I'm saying, but I'll show you. This thing called the coefficient of variation is a kind of Frankenstein statistic. It uses the standard deviation in its calculation, but it also does adds in another feature. I'm just checking that I don't tell you the wrong one. The Chebyshev should be.
Well, the screen went away.
Oh, that's okay. I'll be bringing it back in a second. I'm just trying to find the Chebyshev guy, and he's well and truly hidden. I know he's here. Okay, let me put the screen here for you so you can see it. Okay, coefficient of variation, right? Forget about that, that's coming up later. This is the formula. It's the standard deviation divided by the mean times 100 and converted to a percent. Now, the coefficient of variation, can you see that it's a bit of a monster because it uses the mean and it uses the standard deviation together? And then it makes it a percentage. So I want you to just pretend I've got a data set and I calculate that the standard deviation is 15 and that the mean was 35, just for argument's sake. In that question then, if you're being asked to calculate the coefficient of variation, CV, you just take the standard deviation, which is, oops, get out of here. You take the standard deviation, which is 15, and you divide it by 35, and then you times it by 100, and you get about 42.86%. Now, this particular coefficient of variation, it has very specialized uses. Not many people use it. The most likely people who are going to use this kind of thing are people in business, because it's a number that kind of gives you an idea of not just how spread out the data is, but how spread out it is compared to the value of the typical number. So the typical number is the mean, and how spread out are you compared to that? So in this case here, can you think about 42% spread? It's basically just saying that a standard deviation is about 40% of what the typical number is. Now, a different story. Can you imagine a different data set where the mean was 35, but the standard deviation was, say, 50? Then, in this second world, you'd go 50 divided by 35, and in this second world, you'd get 142.86%. And in a very, very rough way, looking at this data set, what you're seeing is that in this second world, it's 3 times bigger. Now, if I was doing stocks and shares, that would be telling me that if this stock, the amount of money that the variation would cause would be a lot more than if I was using this stock. So this stock is a kind of stock that if you looked at how much it sold for, like every day for a year, you could calculate this, right? And if you imagine this stock every day for a year, wouldn't this stock get you more money, but could lose you more money? It's a very variable stock, price-wise, right? So if you spent, if you spent a lot of money buying it, like 100 shares of that stock, you could lose a lot, you could win a lot. And this stock here would be less variation, right? So if you're into stocks and shares, coefficient of variation, amongst many other numbers that they use, gives you an idea of risk. If I had a CV of a stock and it was 1%, right, for an entire year's of data, wouldn't I be looking at a stock that if I bought it, at least I know next year I'm not going to lose any money. I'm not going to make any money, but that's the kind of stock, if I bought it, I'd be safe. Now, there's another guy out there, it's 400%. If I'm buying that stock, couldn't I like quadruple my money? But couldn't I also end up with a quarter of the money I started with? So that would be a high risk stock. So if you take stock and you collect data, say on a year, whatever you decide is a decent number of data points, can't you come up with this fella and figure out, what's the word I'm looking for? Figure out how risky that stock would be. So if you're interested in why people do it, there's a reason. Now, what's this funny thing up here? It's the Chebyshev guy. They also mentioned that. And it's 1 over 1 minus k squared. And I've forgotten what k is. So I'm going to have to go back in and find out. I believe k is the number of standard deviations away from the mean. But I don't want to tell you something if it's not true. But I believe it is. If I can't find it, then I'm going with that, because I do know it is. For any set of data, if you do k greater than 1, the proportion of data must lie. That's it. So I was right. I'm glad my memory's not that bad. Okay, I've lost you. Where are you? So this little fella uses standard deviations to predict how much of your data. So it's a percentage of data within k standard deviations of the mean. Now, that guy is a decimal, but you convert it into a data. So let's suppose I collect the ages of OC students, and it ends up being 24. And the standard deviation of my sample ends up being 2. The Chebyshev formula will tell me what percentage of the data lies within k standard deviations of the mean. So let's do 1 standard deviation from the mean. Well, that means x bar, add or subtract 1 standard deviation. That's 24, give or take the number 2. So that'll be 22 to 26. So I'm now going to tell you what percentage of OC students, roughly, are going to be in that age range. And according to Chebyshev here, it's, well, can I change this guy to 2? So that's going to be 20 to 28. That's better. Right. According to Chebyshev then, 2 goes here. So 1 take away 1 over 2 squared. Do you realize why I had to change from 1? The formula doesn't work because it says none of the data is in that range. But that guy does work. Isn't that 3/4? Which means 75%. And the answer is at least 75%. Right? It could be better than that. So I know about 75% of OC students are in that range. Suppose I did 3 standard deviations away from the mean. So that would be x bar plus or minus 3 standard deviations. 24, give or take 6. So that would be 18 up to 30. So that would be 1, take away 1 over 3 standard deviations, 1 over 3 squared. That would be what, 8/9, I believe. And 8/9 as a percentage. It's about 89% of OC students are in that range. So can you see how powerful this formula is, the Chebyshev guy? Because all I need to know is the mean, the standard deviation, right? And how big you want k to be. And I can then give you a predictor on the percentage of people in any given range. Let's try that again. Let's suppose that we had a test and the mean of this test was 80 and that the standard deviation in this test was 5. And I would like to know what percentage of students got within 3 standard deviations of the mean. Okay. Well, if you take the mean and you add and subtract 3 standard deviations, you've got 80, give or take 15. So we are looking at what percentage of students were between 65 and 95, right? Well, let's see what that looks like. According to the Chebyshev thing, isn't it that guy? Where key is 3. And that's 8/9. And I had that a minute ago. It's 88%, isn't it? 88.8%, I think, if you want to be accurate. So 89% of all the students in that class are going to get somewhere in the range 65 to 95. Do you see that gives you a little band of, it gives you a good idea of what that class looks like now, doesn't it? I mean, if you take it to its extreme, then doesn't that mean very roughly there's about 11 or 12% of the class that got either bigger than this or less than that? That's cool. Right. Now, connected to Chebyshev, there's a special guy, weird number. It's not standard, but we're using it anyway. It's 2.5 standard deviations. From the mean. This particular interval is very important, so I'll give you a story. The mean of this is 50, and the standard deviation is 20. Do I want 20? I'll make it 500. Yeah, that's better. The mean is 500, and the standard deviation is 20, right? Maybe it's SAT scores or something, right? Whatever. If you do 2.5 standard deviations, you are doing that guy. So you're doing 500, give or take, 2.5 times 20. So you're doing 500, give or take, 50. So that makes a range that looks like that. So what's important about this particular range compared to all the others that you could do, like 1 or 2 standard deviations? It's this. Any number outside this interval is considered a potential outlier. So if I had a whole set of data and it came from here, and you can imagine my data was all the way here and there's maybe a 500 in the middle somewhere, and then there's a guy up here and he was 630. Isn't he outside this range? He would be considered the potential outlier. And at the other side, can you imagine I've got numbers and I've got a guy down here with 300. Won't he also be considered an outlier because he's outside this range? What this allows us to do is it takes the guesswork out of, is that big number at the end really an outlier, or is it just a big number? Right? Or is that little number at the beginning? Is it really an outlier, or is it just a little number, right? Because sometimes, don't you get the kind of gray area where some of you go yes and some of you go no, and it's really not consistent. So this takes the this makes it consistent. Don't you basically just do this? Find the interval. If you're bigger than this interval or you're less than this interval, right? If you're outside it, you're a potential outlier. If you're inside it, you ain't an outlier. You might look kind of big and weird, and there might be a gap there, but it's just, it's just a big number, nothing special. Move along, nothing to look at here.
And that only works with the 2.5?
Yeah, it's 2.5 is the one that they're using. I told you at the start of this conversation, it's non-typical. Do you know what actually number the vast majority of textbooks in me would use? It's 3. You have to be 3 standard deviations away from the mean rather than 2.5. But since this book's using 2.5 and they're going to ask you questions that use 2.5, we kind of bite the bullet and say use 2.5. But in the big world, better to use 3 because that's what everybody else is going to be using. I think we learned some cool stuff today, didn't we? Erica, I either learned some cool stuff or I've figured out how to make you fall asleep. It's one or the other. So you've had a long day, right? I feel your pain. Okay, let's look at this fella. They're taking that Chebyshev thing and doing it in a slightly different way. You've got the mean of 8 and you've got a standard deviation of 4. I'm writing this down. Compute the coefficient of variation. Isn't the coefficient of variation S divided by X bar? Although you cannot see what I'm writing, would you agree that 4 over 8 gets you 50%? Right, S over X bar. So your numbers may well be different, but in this case, it's 50%. Now, here it says, compute the 75% Chebyshev interval. Isn't 75% K equals 2? 1 take away 1 over 2 squared, 1 take away a quarter, 3/4. So basically, they're just saying mean take away 2 standard deviations, mean add 2 standard deviations. So let's see what you get. 8 take away 2 lots of 4 get you 0. 8 add 2 lots of 4 gets you 16. Now, a 75% Chebyshev just means 2 standard deviations. What will an 88.8 Chebyshev get you? Or an 88.9, which is what they're doing in question 11. How many standard deviations for the mean will that get you? One, 2, 3, 4. Not a lot of choices. Definitely don't pick one. I did it 5 to 10 minutes ago. What K value came up with a 88.8, 88.9 kind of number? What K did that?
3.
Yeah, that's what I'm looking for. So aren't you going to do mean 150 plus or minus 3 standard deviations? So plus or minus 9. Oh, and do you notice mean is 150, sigma is 3. Doesn't this mean population mean population standard deviation? But it's the same calculations, the same everything. Are we cool? And I think that is perfect timing. So will you all say hello? Hi, so we can get attendance.